Okay, in this video, we are gonna cover chapter 7, which deals with the central limit theorem. This will be very difficult to follow if you didn't watch the rolling a die simulation video using the StatCrunch. So please watch that first so that you guys can follow the theorem more clearly. Okay, you will have a much better understanding after you watch the video. So I'm gonna keep in mind that you have already seen that simulation. We roll a die with 10 times first, 100 times, and then 500, and I went all the way up to 1,000, right? So this paragraph is a summary of that rolling a die. If you keep larger and larger sample, starting with 10, 100, 500, 1,000, we created two columns and then calculate the mean, right? And then construct the frequency table and then histogram. What happened to that histogram as we increase the sample size? The distribution of our mean became a normal distribution. We had a uniform to begin, and then we went to a normal, right? So your x was a uniform distribution, but x bar is a normal. Now this is a huge thing, a huge connection I want you to make. In the past, all the way up to chapter 6, we dealt with just the x set of sample, 20 sample, 30 sample, and bunch of data value. Now, on top of the sampling, on top of our sample, I'm going to now look at the mean of our sample. So you have a mean, you have a data, could be uniform, could be normal, could be binomial, who knows? So you have a population data value, your sample comes from some kind of a distribution, but it doesn't matter which distribution it comes from, your sample mean will always approaches to normal. That's the whole, that's the key idea of a central limit theorem. To put it more formally, if you draw a random sample of size n, the distribution of a random sample, so we had a x, now you have a x bar, which consists of sample mean, is called the sampling distribution of the mean. The sampling distribution of mean approaches to normal distribution as the sample sizes increases. At the end of the video of our rolling a die simulation, I made 3 comments. The first comment was approaching to normal. That was the first one. The second comment was our mean will become, so your mean of our x ended up being x bar. Remember, it was going to the same mean value, right? 3.5. Okay. And then the third example was we have a standard deviation of a x. This was not equal to our sample standard deviation. It was going on and off. It was a 1.1, 1.2, and then going back to 1.21. It was around 1.2, but there was some up and down. Okay, so notation. Now you're not gonna see an x unless we are talking about just the set of data. Now your variable will be x bar. Your sample mean will always approaches to normal. And there's 2 things that you need to put. The first one was a mean, right, from the chapter 6, and then standard deviation. Now here's the notation that I want you to be careful. Now I'm going to use x bar here, subscript x bar. Why? Because I'm dealing with x bar. So your variable should have a x bar. Now, what is a mean of the sample mean? That's actually a population mean. Mean didn't change. Now, what is a standard deviation? It will be sigma, your population standard deviation, divided by square root of n. So that's why you saw up and down between 1.2, 1.1, and then going back to 1.1, because standard deviation is not a unbiased estimator. Okay, so mean of the x bar, all of these now should be mean of x bar. So your notation will be written as mu of x bar. That's mean of x bar. That will always be your population mean. Standard deviation of our mean, sample mean, will be sigma x divided by square root of n. Okay. Standard error is actually, these two are the same. So some textbook use standard deviation, standard error, it just means sigma of x bar. Okay. So you're going to be putting standard deviation divided by sample size. Okay. Once you can make a distinction between x and x bar, now it's the easy part. You're always going to see a normal distribution, no matter what the size is. Okay, so normal distribution, so finding the probability will follow the same calculator function. It will be normal CDF. So your x bar, right, for the mean x bar, to calculate the probability, because it's a normal distribution, you're gonna press the second key, distribution, number 2, normal CDF, and then just like we did it in chapter 6, you need 4 numbers in the order to put it normal CDF, which is a lower value of the area, upper value of area, and the mean and the standard deviation. I'm gonna put it over here so it doesn't get confused. This will be your mu of x bar, okay, and then standard deviation. Which is your sigma x bar. What is another word for mu of x bar? This is just a mu. Sigma of x bar is right there, this number. Okay. Percentile for the mean will be, percentile, we use the inverse norm, right? So second key, distribution, number 3, inverse norm. Inverse norm from chapter 6, we needed 3 numbers. It was a left area to the left, mean, which is your mu of x, which is just a mu, and then the standard deviation, which is sigma of x bar, which is really sigma over square root of n. Okay. I'm going to make a special note so that I'm not repeating myself. Look back to chapter 6 video for how to enter on calculator. Okay, so I'll type it up the number, I'll write it down, normal CDF and those 4 numbers, but I'm not gonna switch back and forth between the camera and then lecture notes of how to use a calculator, because I already explained it in chapter 6 video. So if you're not sure, go back and then watch the chapter 6 video again of how to enter the normal CDF and then the inverse norm. Okay, let's move on to actual problem. Example 1. An unknown distribution has a mean 90 and standard deviation 15. Sample of size n equal to 25 are drawn randomly from a population. Find the probability that the sample mean is between 85 to 92. So couple things. I have a word probability. Now I don't see an x. Now your variable is a sample mean. So finding the probability, so that has to do with normal CDF. Okay, again, there's only 2 functions, normal CDF or inverse norm. Okay. So we will be using the normal CDF because it's calculating the probability. So let's take a look. We don't know what the distribution of our sample is, but it doesn't matter. It could be uniform, it could be something else, but whatever the case is, you're always going to have a normal distribution for the X bar. That's the central limit theorem. So this is what it's interpreting. Find the probability. Okay, probability of what? Sample mean. Notice I am using X bar now. It's not X, it's a sample mean. Your variable is X bar. Between 85 to 92. I'm going to draw out my curve. This has a mean 90. So if I'm looking at 85, I should grab something like this much area, right? 85 here and then 92, a little bit past 90, so this much area. I should have a, right? So let's check. All right, this will be a normal CDF. You need a left value, so my area begins at 85 all the way up to 92. Your mean is, what's your mean? Well, this that I drew was your right, so this one right, this over here, I have 85, 92. Our mean, this over here is given as a mu of x 90, and then standard deviation is 15. This is not your x bar because it tells you right there an unknown distribution has a mean 90, standard deviation 15, and we had those 25 samples. So to calculate the x bar, right, this was given as just a mu right here, the first one. Standard deviation is calculated as a sigma of x divided by square root of x. So if you use these two, you're using an x one, x, not the x bar. I'm looking for sample mean, so we have to calculate it. So this will be just same value 90, and then sigma of x bar is sigma over square root of n, which is equal to 15, and we have a sample size of square root of 25. Let's simplify. Square root of 25 is a 5, so this reduced down to 3. So you're gonna put 90 and then 3 here. So that's what I want you to be careful. This number and this number. This number will be always the same, but this number, the standard deviation will be different. Okay. So you're gonna put that in the calculator. Second bar's normal CDF. I'm getting 0.6997. Okay. Right? So don't forget, our variable is x bar. So your mean and standard deviation should be one with the x bar, not with the x. So don't use the x because our variable is x bar. How did you know that it was x bar? It tells you right there, sample mean. Okay, so you're looking for the keyword sample mean. Let's try part B. Find the value that is 2 standard deviation above the expected value. Okay, so I'm looking for K. That is 2 standard deviation of expected. Remember expected value from chapter 3? Another word for expected is a mean. So basically whatever mean that I have, I am adding two standard deviation above. 2 standard deviation above. Okay. All right, so that's it. So I have sigma mean of the sample mean as a 90. Adding 2 standard deviation, we calculated, x bar. The X bar was a 3. So I have 96. Okay. Again, how did I know that I'm dealing with the X bar, right? Right there. The problem says sample mean. So I have to use the sample mean of the sample mean, and then standard deviation of the mean. Part C, find the percentile. So this is a percentile question. That's a finding the inverse norm. Area to the left, mean, and the standard deviation. So inverse norm, since they give you the area to the left already, 95, I don't have to find out the other one. It will be 0.95. Remember, it's the sample mean, so I have to use 90 and then 3, not 90 and 15. That was for the X. 90 and then 3. Using the calculator, I'm getting 94.935. Okay? Since we talked about z-scores, the problem might ask you the z-score. I'll give you the formula for the z-score too. But z-score will be the same thing. So z-score can be calculated as x bar minus mean of x bar over standard deviation, which is sigma over square root of n. Follow same structure. Right, let's try working on exercise 2. This is a homework number 7. Okay. All right. So the distribution of income in third world country is considered wedge-shaped. Many very poor people, very few middle income people, and even fewer wealthy people. Suppose we pick a country with a wedge-shaped distribution. So it really doesn't matter what the distribution of our sample, right? But this happened to be a wedge-shaped distribution. It's just telling you some extra information, like a uniform distribution. The average is given. So this average is your mu of x, the variable x, 2000. Because anywhere in the sentence, you don't see the word sample mean. So this is all information dealing with the x, not x bar. Okay, so don't get confused. Again, standard deviation, you don't see a word sample mean. So that's just sigma of variable x. That's 7,000. We randomly surveyed 1,000, so that's your sample size, 1,000. Okay, in words, define the random variable x. So what is our x represent? X was a salary, right? So the number of people will be n. The number of people, again, the number of people always, that's just n. Yearly income for someone in the third world country, yearly income for each person in a third world country. It will be, the correct one will be the third world country, so it will be this one. Someone in a third world country. We didn't get each person in a third world country. We picked some of the third world country and got the result. So yearly income for someone in a third world country. In words, what will be the x bar? See, the problem is really testing you to see if you know the difference between x and x bar. X was a yearly income. X bar will be the mean for that. So you have the mean. So I'm looking for some average. So all of them has an average. So let's do the process of elimination. Average salary from a sample of 1,000 people throughout the country. The average salary from sample of 1,000 residents of third world country. The average salary of all, we can definitely eliminate these two. All resident, we didn't get what, we only have 1,000. So it wasn't all. So A or B. The average salary from a sample of 1,000 people throughout the country, or third world country, it's third world country. The original problem right there. Right, we have just the third world country. Okay. Now I know it didn't ask for this, but let's kind of set up the problem since part B. Now your mu of x bar, right? Sigma of x bar. So mu of x bar is same thing as mu. So this will be still 2000. Remember, rolling a dice problem, it was approaching to 3.5 each time. Sigma of x bar is not 7,000, it's a sigma divided by square root of n. Same idea. Depending on the number of sample size, the standard deviation kind of slightly vary, going up from 1.2 to 1.1 and going back to 1.2. So that's why we have to do divided by the sample size, because it varies depending on the sample size. So standard deviation, 7,000 divided by 1,000. And that's in fact part C. X bar will always be a normal distribution. And then you're going to be putting first one, mu of x bar, which is our mu, and then standard deviation for the second one. So these two will be going in the parentheses. But it's asking you to round it to the 2 decimal place. So let's change this number to 2 decimal place. I'm getting 7,000 divided by square root of 1,000, 221.36. So I have a normal distribution with 2,000 and 221.36. How is it possible for the standard deviation to be greater than the average? Okay, for these, I think process of elimination is the best. So let's go through the very wide difference in data value can have average smaller than standard deviation. This is an example of a poor survey. The average should never be smaller than the standard deviation. The very small difference in the data value can have average smaller in the standard deviation. What is a standard deviation in general? It measures how the data varies from the average, right? So part A right there. Very wide difference in the data value can have average smaller than the standard deviation. It's just definition. What is a standard deviation? It measures the difference in the data within the average. Okay. Part B, we cannot really say this is a poor survey because you didn't really go through and then saw the all errors. We are just given the information, so you cannot assume that this is a poor survey. Okay. Part E, why is it more likely that the average of 1,000 residents will be from 2,000 to 2,100 than from 2,100 to 2,200? The sample size was sufficiently large to ensure the sample mean close to the population mean. The distribution of the sample mean will have a higher probability closer to the population mean. It is actually more likely that the average of 1,000 residents will be from 2,100 to 2,200. Because the standard deviation is so high, there is a high probability that the sample mean is close to population mean. First, let's eliminate the obvious one. Sample size was sufficiently large. Well, 1,000 seems a reasonable number, but we haven't really checked that it was a sufficiently large in comparison to the all third world country. You cannot assume all those extra things if you're not given. So I can eliminate this. I don't know. Maybe 1,000 was sufficiently large or 1,000 was not. The number seems big enough, but in comparison to how many third world country there are and how many residents there are, maybe it could be small. So I'm going to eliminate the first one. Because the standard deviation is so high, there is a high probability that the sample mean is closer to population mean. Standard deviation doesn't really, it only measures, remember, standard deviation is just a distance, right? One standard deviation, this distance, 7,000. Whether it's large or small, it doesn't affect any probability because it only measures how much data is away from the mean. So this doesn't make, that also doesn't make sense. So we are left with the second one or third one. It is actually more likely that the average is 1,000. We don't know. The average of 1,000 will be from 2,100 to 2,200. We just measure, we got the result that it was a 2,000, right? 2,000 here, 2,000. So I don't think the mean will change from 2,000 to 2,100. So the best one will be the second one. Distribution of the sample mean will have a higher probability closer to the population mean. That was the fact, right? Sample mean, right? Our sample mean, we had, with the large enough sample, it keeps switching to normal distribution. Okay. All right. Next one. This is a central limit theorem for sum. Now, first one was for the mean, average. Okay, I call this CLT number 1, dealing with average. So your variable is X bar. Now you can do the similar thing with the rolling a die. Instead of looking at the average, I can just sum up the value, and that's a central limit theorem number 2. Your variable now deals with the sum. So your variable is not X bar. Your variable now is the sum. The sigma notation in mathematics is the sum. Okay. So I didn't illustrate it in the last video, the central limit theorem video with the rolling a die, but from sample mean, I can calculate the sum, and then you'll see the similar idea. You're going to have the distribution of data of the sum approaching to normal distribution. The central limit theorem for the sum says that if you keep drawing larger and larger sample and taking their sum, the sum of their own normal distribution, the sum of their own normal distribution, which approaches to normal distribution as the sample size increases. In other words, if you draw a random sample of size n, and then as n increases, the random variable sigma x consists of sum tend to be normally distributed. And the notation that we will be using is now sigma x, not x bar, sum. Why? We are looking for the sum. It's going to be approaching to normal. So you have the notation that we will be using is mu of sigma x, standard deviation of sigma x. How do you calculate that? Well, I better have, if you're summing up, your mean average will be a lot bigger too, because you keep adding. So this sigma of sum of x is not equal to population mean. It will be a lot bigger number. Okay. So this is equal to, I'll give you the formula, n times sample size times our population mean, and standard deviation will be square root of n times sigma of x. Okay. A random variable has a following z-score, so this is a normal distribution, so you can also calculate the z-score. So z-score will be sum of x, our variable, subtract n minus mu of our x divided by square root of n sigma of x. This basically means it follows the same thing as x minus mean and then standard deviation from chapter 6. There's your variable. Here's my mean, which is here. And then the bottom one is a standard deviation, which is our standard deviation for the sum. Okay. Again, chapter 6, it's a normal distribution, so find the probability. We are going to be using the normal CDF. Finding the percentile for the sum, we will be using inverse norm. So second distribution. And then it was a number 2, normal CDF. We need to enter 4 numbers in the order. Normal CDF. First number, lower value of the area. Upper value of the area. Our mean of the sum. And then last number is a standard deviation for the sum. So those 4. But mean for the sum can be calculated as n times mu of x. And then standard deviation is square root of n times mu of x. Percentile will be inverse norm. Number 3. K equal to inverse norm. Area to the left. Mean, which is n times mu of x. And then standard deviation, square root of n times sigma of x. Okay. Again, please refer to chapter 6 on how to use a calculator. Okay. I'll write it down what you need to enter, but putting into calculator, you can go back to chapter 6 videos. All right, so let's, there's 2 more exercise, example 1 and 2 for the central limit theorem, number 2, and then we'll go to the last section. An unknown distribution has a mean 90, standard deviation 15. A sample of 80 is drawn randomly from population. Now from this description, you don't see the word sum or mean of mean, sample mean, or anything. So this mean is just your regular x. And standard deviation is your x variable. We have a sample size of 80. Find the probability that the sum, take a look at the word sum. And then you're looking for probability. So I'm calculating the probability. But what's your variable? Your variable will be the sum now. Okay? So your variable now deals with the sum. Okay? Notice earlier you see the word mean. So I use mean variable. Now you see the sum, so I use a sum variable. So be careful when you're reading the question, because the problem will not tell you, oh, this is a sum, central limit theorem number 1 or central limit number 2. You have to decide. And then what are you looking for? You're looking for keyword, either sum or the mean. I want that to be more than, so I want greater than, 7,500. Okay. All right, so let's do that. On the side, I'm going to calculate my mean for the sum and then standard deviation for the sum. Mean for the sum, from previous page, it was n times mu of x. N is 80, so 80 times 90, which give you 7,200. And then standard deviation for the sum is equal to square root of n times sigma of x. So I have square root of 80 times 15, which is equal to 134.1644. 1641. Okay, so this is what's going on. You have a mean. Normal distribution. Mean is right in the middle, 7,200. I'm looking for 7,500 and more. I'm expecting an error, the probability value less than what? 0.5 for sure, because I'm not even shading half of the curve, right? Let's check. So we will have normal CDF, because this is a probability, normal CDF. Lower value, that's this one right over here, which is 7,500, right? Because we want greater than 7,500. So that will be my lower bound. Upper bound will be 10 to the 99 because it's going all the way up to the really large number. Mean, now your mean, don't forget, we are dealing with the sum. So you want to use 7,200, not 90. 90 was your x. You are dealing with the sum, so you want to use the sum mean of the sum. Okay. 7,200, same thing. Standard deviation is not 15 because it's not x. I'm looking for the sum, so I want to use 134.1641. I'm getting from the calculator 0.0127. Okay. Find the sum that is 1.5 standard deviation above the mean of the sum. Okay, so we're looking for some sum value such that you have 1.5 standard deviation above the mean of the sum. Okay, so mean of the sum, whatever mean of the sum is, I want to go 1.5 standard deviation above. We have these two numbers ready. 7,200 plus 1.5 times 134.1641. So final answer, I'm getting 7401.2. Okay. Right, one more. Number 9, suppose that the duration of a particular type of criminal trial is known to have a mean 18 days, standard deviation of 6, sample of 9. All right, another, be careful, your mean. You see that in the sentence, there's nothing that says sample mean or sample sum. So this is just mu of x equal to 18, the variable x. Standard deviation x equals 6, and then sample size of 9. In words, what is x, sum of x mean? Sum, that's a sum formula, so I should see a word sum, or total is another word for sum. What are we looking at? What was our x value? It was a criminal trial, number of criminal trial. So I'm looking for not all trial. I'm only looking for sample of 9, so I can eliminate this one. It's not total number of hours. It was just days. It's given as a days, so it doesn't make sense to have an hour. It's not a total number of type of a trial. It just say duration. So it will be this one over here, total number of days for the 9 trials. Notation, the sum of x will approaches to normal, and your sigma, mu of sum, and then sigma of the sum will be there. So mu of sum formula says n times mu of x, which is 9 times 18. I'm getting 162. Sigma of the sum will be square root of n times sigma of x, square root of 9 times 6, 18. Part C, find the probability that the total, you see the word, look for the variable. Are we dealing with x? X bar or sum? How do you know? I see the word total, so it's a sum. So find the probability for the total. At least means what? What is the word at least? I want that to be greater than or equal to 198. Yeah. Okay, at least. All right, so this is finding the probability, so normal CDF. Lower bound, our mean was a 162, so 198 is right there and on. So 198, 10 to the 99, mean will be 162, and then standard deviation is 18. Using the calculator, my area or the probability value, I'm getting 0.0228, rounding to the 4 decimal place. Okay. Part D is a percentile question. You're given the percentage, you're looking for K. 60% of the total of, oh, I see the word total, so now you're dealing with the sum of X. Of these types of trial will last at least how long? All right, so again, there's my 162. I'm looking for at least, right? So I want the sum to be at least means greater than some kind of K value. That's given as a 60%. That's what it means. You are given the 60% of what? Some random value K that you want that to be such that it's bigger than 0.6. So let's take a look at it. This is a halfway mark. So if I shade it in, that's a shaded up to this 162, that's 50%, but I want 60. So I should go a little bit lower. Grab 60. So this will represent 0.60, whatever this number K, right? That's what I'm looking for, the number of days. What is the number such that greater than, because at least this one and on represents 60%. Well, so K is equal to inverse norm. Here's where it gets a little bit tricky. Remember, first number is area to the left. Area to the left. So do not put 60. You should really put what? 0.40. Why? Because this is area to the right, because I want greater than. I want less than on the calculator, because it's area to the left. If you have function of selecting the tail, remember I show you in chapter 6, you can use 0.60, but make sure you put the right. But if you don't have option, you have to put 0.40. 162, that was your mean of the total. And then 18, I'm getting, rounding to the 2 decimal place, 157.44. Okay? All right. So that's chapter 7.1 and 7.2. Now 7.3 is not difficult. 7.3 is review of chapter 7.2, 7.1 and 7.2. It just give you a problem, kind of mix it up. 7.1, we only look at the sum. We looked at the mean, right? And the mean. 7.2, we looked at the sum, total. Now 7.3 is just mixing up CLT number 1 and CLT number 2. So it's really testing you, oh, do you know the difference between the CLT number 1 and CLT number 2? Which it's really easy. How do you determine the difference between the two? If you are being asked to find the probability for the mean, you just have to look for the keyword mean, which is the X bar. Then you're going to be using the CLT for the mean, the CLT number 1, which is 7.1. If you are asked to find the individual value like a X, then don't use CLT value. Use a uniform or use whatever the distribution is. Now, if you are being asked to find the sum, then it will be CLT number 2, which is 7.2. Okay? So that's what we are going to do. They're going to switch back and forth between X bar, X, and then the sum of X, and you have to be keeping organized and decide which one is which. Example 1. A study involving stress is conducted among the students on a college campus. The stress score follows a uniform distribution with the lowest stress score equal to 1 and highest equal to 5. Using a sample of 75 students, find. Now, just reading off this description, this is all the information about the X. How do I know that? You can read through one more time. I don't see a word mean or the total. Okay, so this is all information about X. So I'm just gonna write down what I know to keep it all separate. I know X comes for uniform distribution. This will come handy, okay? So let's label all those. This uniform distribution, recall chapter 5, it was A, comma, B. Lowest 1, highest 5, so 1, comma, 5. And we have a sample of 75. I know it didn't ask for this, but let's calculate our mean. Okay? Because we need to eventually use our population mean and then standard deviation to calculate CLT 1 and 2. It was A plus B divided by 2. Right? So A plus B divided by 2. So I will have 1 plus 5 divided by 2, which is equal to 3. Standard deviation for the uniform distribution. Remember, X is a uniform, so I have to use a uniform distribution formula. B minus A squared over 12. So I have a square root of 5 minus 1 squared divided by 12, which equals 1.15. Okay. Part A, I'm going to highlight 2 keywords, and that's what you really want to look for, 2 keywords. What are you asked to find and what variable am I dealing with? Probability. My variable, mean. Oh, they give you the percentile. Oh, my variable is mean again. Oh, part C, I'm asked to find the probability. Oh, my variable is total. They give you percentile. My variable is total. If you can find that keyword, you're pretty much done. A is to find the probability. So I'll be using normal CDF with CLT number 1. Why? Because this deals with the mean. Mean, CLT number 1. Percentile, that's inverse norm. Okay. What are we dealing with? CLT number 1, because we are dealing with a mean. Probability, that's normal CDF. Total, CLT number 2, that's a sum. Percentile, inverse norm. And CLT number 2 because it's a total. So that's pretty much it. So if you can determine the 2 things, what function do I use? Like normal CDF, or is it an inverse norm? And then the second question that you want to ask is it CLT number 1 or CLT number 2? So So let's calculate all those numbers. So when we plug it into the calculator, we have all the numbers ready. So let's do X. I'll use different color. X bar, that's CLT number 1, right? It will be always normal with mean of our X, right? And then standard deviation is sigma over square root of n. So this is equal to 3. And then where's the 3 coming from? Your mean of X will be same thing as your population mean. Standard deviation will be 1.15 divided by square root of n, which is 75. I like to leave it like this way so that I'm not rounding. Okay, so you can put it in a fraction too on the calculator. And the last one is CLT number 2. That's dealing with the sum. Sum also is a normal. Mu for the sum and then standard deviation for the sum. Mu for the sum was n times mu of x, and then standard deviation was a square root of n times sigma. So sum will be equal to 75 times mu of x, that's 3, and then square root of 75, our sigma was 1.15. Okay. So I'm just gonna make this number a little bit better. 75 times 3 is a 225, and then we have 9.96. Okay. All right, let's begin. Part A. We have all those ready, normal CDF. 4 numbers. What are we looking at? Oops. In fact, let me put this one over here. We are looking for, I want to use a notation probability that the mean test score X bar is less than 2, Okay. All right, so I want less than 2. So whatever the curve is, and the mean was a 3, right? Mean was the 3, less than 2, I'm shading all the way here. So I have a lower bound as a negative 10 to the 99, upper bound all the way up to 2. Mean for the sum, the correct one is this one here, mean for the sum, CLT number 1. So 3, and then this last number. 3, and then 1.15 divided by square root of 75. If you have this all set up, even though they didn't ask, this is a lot easier. Now I can look and then see, oh, is it this number or is it this number, this number, this number? If we're trying to do this all in one step, it gets confusing. So I want you to do this each time. X bar, sum. After you label all this, pick the correct one, X bar, so I'm using these here. All right, so calculating, I have 0, okay, 0%. Does it make sense to have a 0%? We didn't really had 0 in the past. Well, think about this. You're looking for the average score to be less than 2. well, you have a lowest test score equal to 1. So if you are looking for, you know that not everyone will always have a score of 1, right? Some people might have a higher stress score, so some might have 3, some might have 4, some might have 1, some might have 4, 5. So if you average all those numbers, it will not be less than 2, unless all the data value will be always equal to 1. So that's why it makes sense to have a 0%. Part B, 90 percentile for the mean. So this is a percentile. So K value, inverse norm. Since it's a 90 percentile, that's a lower area that's given. So 0.90, again, we use 3 and then 1.15 over square root of 75 because we are dealing with the mean. I'm getting K equal to 3.2. Let's try part C. Going back to the probability, we already know to ourselves normal CDF with the CLT number 2. So we have probability for the total score less than 200. Our average here was 225, so I have lower going to the left. So I should have less than 0.5 for sure. Okay, let's check. Normal CDF, lower bound, I have infinity, negative 10 to the 99, all the way up to 200. My mean and the standard deviation is now dealing with CLT number 2, so I'll be using these two numbers because we are dealing with the sum, right? 225 and 9.96. 225, 9.96. I have final answer using a calculator, 0.0060. Last one, part D. We have a percentile K, so inverse norm, given as 0.90. Again, I will be using 225 because it's a total. 9.96. Got my final answer as 237.8. Okay. All right, one more practice. This is a homework problem number 13, but it's dealing with the exact same thing, determining whether we are dealing with x, x bar, or the sum. Okay. Suppose that the length of a research paper is uniformly distributed from 8 to 27 pages. We survey a class in which 55 research papers were turned into a professor. The 55 research papers are considered random collection of all paper. We are interested in the average length of a research paper. All right, so you see that all these information is your x, because I don't see a word anywhere here, sum or the mean. So let's do some labeling. You have uniform distribution, so your x deals with the uniform distribution, a comma b. So your a will be 8 to 23, mean to max, right? And then we have what else given? Sample size 55. All right, part A. In words, define variable x. What are we looking at? We are looking at length of a research paper in what unit? Pages. So let's do that. Nope, not a number of not a number of students, that's a sample size. Not number of words, it's a length in pages. Not the number of this one right here, number of pages of research paper. Oh, we already have the second one done. Distribution of x right there is a uniform distribution. Uniform distribution 8, 23. Uniform distribution comes from chapter 5. So if you do not remember the setup, it was A, the minimum number, and the maximum number. Okay, This, notice you see the variable here, it's the x. So I want to calculate the mean from the uniform distribution. So your mu of x is a plus b divided by 2. Your standard deviation for the x, since it's a uniform distribution, you use the uniform distribution formula, b minus a squared over 12. Plug it in, 8 plus 23 over 2, 15.5. Sigma of x, that's 23, take away 8 squared, 12. Using the calculator, I got 4.3301. Okay, and then 4.3301, rounding to the 4 decimal place. So x represents the number of pages. What's x bar? X bar is a mean, average. So it will be average number of pages, right? You just follow this one, but just add word average. You know, by central limit theorem number 1, this is CLT number 1, right? Because it's an average. It's going to be a normal. And the first number was a mean. And then second number was sigma over square root of n, right? These are all your, comes from the x. So so mean will be the same, 15.5. Standard deviation will be 4.3301 divided by square root of 55. Asking you to round it to the 3 decimal place. I'm getting 0.584. Part G. In words, define the random variable for the sum. Oh, now I have a sum. CLT number 2. So this will be just same thing. Instead of average, you're going to have a total number of pages. Of what? Your 55 sample. Okay. Not the research paper. We are given specifically sample of 500, not the entire professor's class. So the first one is the correct answer. Notation, it will be a normal distribution. Your mean for the sum was calculated as n times mu of x. Standard deviation for the sum was calculated as square root of n times sigma of x. So 55 times 15.5, I'm getting 852.5. Standard deviation, square root of 55. Sigma of x was a 4.3301. Right over here, sigma of x. So my final answer, I'm getting 32.113. We have all of them set up. Let's finish the last few more questions. Let me do J first and go back to I and K because I want to do all the calculation first and then do the interpretation afterwards. Calculate the probability that the professor needs to read total. Okay, again, look for the 2 keywords. Probability, I'm calculating the probability, and I am doing the sum. So this is normal CDF with what? CLT number 2 because it's a total. Okay, more than, so probability of the sum to be more than 930. From part H, the sum, the mean was 852.5. So 930 is to the right of it, so I expect less than 0.5. So normal CDF, lower bound 930, upper bound 10 to the 99, 10 to the 99, and then we have mean as CLT number 2. So I'm looking for these two answer right there, CLT number 2, a 52.5 and 32.113. Final answer, using the calculator, normal CDF, entering 4, I get 0.0079. Okay. All right. Last two questions, going back to I. Without doing any calculation, do you think that it is likely that the professor will need to read total of more than 930 pages? Why? The first option is the distribution is uniform with the mean 15.5 pages, making highly unlikely that the professor will need to read more than 930 pages. It is likely that the professor will need more than 930 pages because it's possible that all 55 students wrote 20 or more pages. Well, 20 or more pages, I'm not sure where the 20 comes from, so I can eliminate the second option. I just know that it's length of 80 to 23, right? That doesn't mean all the students wrote 20 or more. I could have 8 pages, right? A lot of 8 and 9 pages, right? So who knows? But first fact is for sure, I know it's a uniform distribution. It was given on the problem. And it was a correct mean, 15.5. We have 15.5. It is high, so best option out of the two will be the first one. Okay, why is it so unlikely that the average length of a paper will be less than 10 pages? Let's do the elimination. Let's do the process of elimination. There's no evidence that a student handling a paper with less than 10 pages. The mean page length and the range in length make it unlikely that most of them are less than 10. A 23-page paper is an outlier, which will make higher average since 50% of the paper is below the mean. All right, I know that I can eliminate the third one for sure. 23 page is an outlier. 23 is max. Remember, it's going from 8 to 23. So it's not necessarily an outlier. Outlier is an extreme value. That's not a high outlier is not always the highest value of the data, right? We saw back in chapter 2, IQ score, the highest data wasn't an outlier. So I know I can eliminate this. Let's look at the fourth one. Since 50% of paper are below the mean, well, what is our mean value? Our mean, original mean from the data was 15.5. So if you are dealing with 15, the variable x, 15.5, less than 10 pages is here. It's not 50%, it's less than 50%. So I can eliminate this one as well. There's no evidence of a student handling in a paper with less than 10 pages. The mean page length and the range in length make it unlikely that most of them are less than 10. Which one is a better one? There's no evidence of a student handling in paper with less than 10 pages. That one doesn't really tell you a lot of information. It just say, I don't know if it. In other words, the first option is telling you that we don't know if student handles in a paper less than 10 pages. That's what it's saying. The second one says the mean page length and the range of a length make it unlikely most of them are less than 10. Well, mean was 15.5. The range was 23 take away 8. Remember, the range is a max minus the mean. So 23 take away 8 will give you 15. Okay. So second one is the best one. The mean page length 15.5 and the range is 15. So the difference, right, makes it unlikely that most of them are less than 10 pages. We got both 15, around 15. So the second one will be the best option. Okay, so this was chapter 7, central limit theorem number 1 and 2, and then decide which one to use. Depends on the word, either mean or the total. Okay, I'll see you in chapter 8 video.